Hello everyone, I'm Dan. In this tutorial I'm going to talk about resistance. So let's get started by opening up our web browser to my website, thegpu.com. I'm going to scroll down here to the electronics tutorials and select the third option here, resistance. Now let's talk a little bit about, first off, sharing versus non-sharing elements. The periodic table of elements represents the atomic weight of every element known to mankind. Now, certain elements don't mind sharing their electrons with each other. Silver, copper, gold, and aluminum are all at the top of the list. While every element prefers to just sit there and be content, these elements offer very little resistance to exchanging one electron for another. In my previous video, amperage and voltage, I touched on the relationship between amps and volts and then proceeded to fry an LED. I powered the LED using a benchtop power supply, which allows me to control the maximum output voltage and the maximum output amperage. Now, benchtop power supplies are great for learning and testing circuits, but ultimately the end product will most likely be powered by a battery, power adapter, or directly into an outlet. If we want to power a 3-volt 20 milliamp LED, which was what I used for which is what I fried back here on this one here, using a 9-volt battery, then we must be out of luck, right? Now, in the amperage and voltage video, the LED fried at around 6 volts, so wouldn't it be nice if there was a way to somehow decrease the amount of electrons flowing without decreasing the voltage? Well, I'm going to take a little quote out of The Godfather there with the "I'm going to make him an offer he can't refuse." And I'm not going to try to do the imitation of that. I'll just end up sounding really stupid. But anyway, while silver, gold, copper, and aluminum offer very little resistance to exchanging electrons, other elements simply prefer not to share. Elements such as carbon really like the electrons that they have, and openly sharing is just not in their nature. Now, while carbon may not like the idea of sharing an electron here and there, it can be coerced into sharing an electron by applying a little more muscle from our enforcer, Mr. Voltage. That's in case you didn't catch that, that's my little godfather. Anyway, whatever. If Mr. Voltage applies 9 volts of force to one end of a copper wire, then pretty much 9 volts will come out of the other side. However, if Mr. Voltage applies 9 volts of force to a carbon rod, then the collective resistance of the carbon atoms will make the flow of electrons across the rod way more difficult. Now, this means that fewer electrons will pass through a point during the time it takes for 1 second to elapse. If you remember that, that's the very definition of amperage there. Now, when that happens, the amperage drops across the rod, and the rod eats some of the voltage as well. Well, sort of. Okay, I'll explain a little later in the experiment. Now let's talk about resistance. Now that we understand the concept of resistance, we can now add another unit of measurement to our tool belt, and that's the ohm, and this is the symbol for the ohm. Now, the ability to provide resistance is measured in ohms. Amps, volts, and ohms are the 3 amigos of electricity, and here is their relationship. 1 volt is the force required to move 1 amp across a conductor with 1 ohm of resistance. Okay, it's just that simple. The ohm. Now, in the world of electronics, a volt is abbreviated as E or V, and ampere or current is abbreviated as I, and resistance is abbreviated as R. Okay. The ohm is named after a German physicist, George Ohm, and that's not misspelled, by the way, either, who discovered the fundamental relationship back in 1827. He came up with an incredibly useful formula, and here's how it goes. Amps equals volts divided by resistance, or I equals VR, if we're using the abbreviations. We apply a little algebra, V equals I times R, or R equals V divided by R. Now, all the equations above are equivalent. Just rearrange algebraically to come in. This should be handy in different scenarios. Okay, so in this particular one, we're going to use this, this form of the equation right there. So we want to find out what sort of resistor we want to put on this. So what we're going to do is we're going to take 9 volts, which will be coming out of the benchtop power supply, or a 9-volt battery, right? Minus the 3-volt tolerance, or the rating of the LED, and we're going to divide that by 20 milliamps, which is 0.02 amps. Okay? Now, if we just run this through our calculator and do 6 divided by 0.02, we come up with R equals 300. So a 300 ohm resistor should do the trick, but the closest thing that I have is a 330 ohm resistor or a 220 ohm resistor. And in future tutorials, I'll kind of explain why there's such a weird, strange gap in the numbering of these resistors. But for now, let's just go ahead and go with the 330 ohm resistor, which has more resistance than we need. So the amperage is going to be less than 20 milliamps, and that's fine. So no problemo there. Okay, so let's experiment a little and not fry an LED this time around. So I'm going to go ahead and just, let's minimize that, and I'm going to bring up my little camera here, and I'll just go and maximize it there. I've got my multimeter, my digital multimeter in here today, and then same power supply from yesterday. Now I've got the 330 ohm resistor hooked in right here, and maybe I don't need to zoom in on that today. And then a brand new, fresh, non-burnt up white LED here. 20 milliamps is the rating on that, 3 to 3.2 volts. And let's go ahead and turn this on, but no power is applied yet. I got my voltage set to 9 volts with a maximum amperage of 1 amp, right? So we know from the last video, this is more than enough to fry this LED, okay? Now let's see what happens when I press the on here, okay? The LED turns on, right? But as you can see, the amount of current, the amperage going across there, is only 18 milliamps, okay? Well, that's kind of weird how that's got out of cycle there on that. It's strange. Anyway, let me bring that down and bring that back up and see if it's still doing it. It's just some sort of weird cycle thing with it doing that little funky thing there. What I'm actually going to do is, because I really find that kind of annoying, is give me a second here. I'm going to pause this video and fix that. Okay, something got out of phase, and that was really weird and annoying there. Okay, let me turn the power back on there, right? And so we basically have 16 milliamps of current flowing through the whole entire circuit there. So let's just explore a little bit on what's going on. And now it's doing that weird stuff again. But that is super bizarre. There we go. It's never done that before. All right, so I'm going to turn on my digital multimeter here. And what I'm going to do is I'm going to hook it in first, in between. I'm going to measure the current going across the LED. And I'm just going to do that simply by putting this there like that, right? And then this right over here like that, okay? Now you can see it's showing 3 volts there going across there, which is exactly what we're looking for, right? So that's well within the specs. As a matter of fact, it's spot on the spec there, okay? The next thing that I'm going to do here is go ahead and put these across the resistor. Okay. Oop, oh my God, this should actually be over here, and the negative should be on this side. Okay, so what we're seeing here is 5.96 volts, approximately 6 volts. And this is just what's called basically a voltage drop across the resistor. So the resistor is kind of like, you know how I said it was eating voltage, right? It is sort of. It's consuming like 6 volts of electricity, so that the remaining 3 volts is exactly what we're sending through the LED there. Now, if I take and I move the probe over to here, right, what we're going to see is we're going to see the, the 9 volts approximately that's coming across there. It's very close, right? 8.98 volts flowing through the whole entire circuit. All right, so that, I'm just going to kind of leave it at that for this tutorial here, and I'm gonna go into a little bit more depth on voltage drop and forward voltage drop and stuff like that in my next tutorial there. Anyway, I'm going to go ahead and let's just turn that off. And we'll turn that off. I'll minimize that, and that'll conclude this tutorial. Thanks for watching.